Now, a lot of times we are not just concerned with how much work a certain amount of energy can do, but also how quickly the work can be done. Power is the rate at which work is done or the rate at which energy is transformed. Anytime you define something as a rate, it is divided by time. The label ends up being joules per second, but it has been given the name of watt. You probably recognize this label as it is most often associated with electrical power, but it is also used to describe other energy transformations. Another representation of power you may be familiar with is the horsepower. James Watt needed to relate the power output of his new steam engine to something people at the time were familiar with. He determined that a good horse could work all day at a rate of 360 foot-pounds per second. So as not to be accused of exaggeration, he took his value half again as much and defined it as 1 horsepower. So 1 kilowatt of power is roughly equal to 1 1/3 of a horsepower. Now, it is important to make the distinction between energy and power. You are limited by how much work you can do, not only by the total energy required, but how fast you try to do it. Say you take a walk down the block. You are expending a certain amount of energy, and at the end, you may or may not feel a little bit tired. However, if you sprint down the block, there is a noticeable difference in how you feel because your body has expended that energy at a much higher rate. So what is the power output for a 60-kilogram woman who is running up a 3-meter high flight of stairs in 3.5 seconds if she starts from rest and ends with a velocity of 2 meters per second? Well, we're looking for power, so let's start with that. The work we are doing is in the form of mechanical energy, both kinetic and potential, so the total work done is the kinetic energy plus the potential energy. We know those expressions for kinetic energy and potential energy, so we can substitute those in here and plug in our numbers. For this flight of stairs, the woman's power output is 538 watts, or about 1 horsepower. Energy consumption and efficiency is a pretty big deal. If you look at your electricity bill, you will see that you are typically charged for a certain amount for the number of hours that you are using power. The rate is based on what is known as a kilowatt hour. Most appliances now come with an efficiency rating that gives you a good idea of the amount of energy it will use, and sometimes even how much it will cost to run it per year. So what is the cost of running a 0.2 kilowatt computer for 6 hours per day for 30 days, if the cost of electricity is 12 cents per kilowatt hour? We are looking for the cost of running our computer. This cost is based on how much energy the computer consumes over the course of 30 days for 6 hours per day. The power used is the energy per unit of time. So we can determine the amount of energy used by taking our power rating and multiplying it by our time. We find that this gives us 36 kilowatt hours of energy this month. If you are charged 12 cents for every kilowatt hour, the total cost to run your computer is $4.32 per month.